not a new thought. Graphs of logarithmic functions. So a logarithmic function is a function of the form y is equal to a log, this is called base. So remember with exponential functions, we had a base, the base of the exponential function. Well, log functions are related to exponential functions, so the base is the same base, right? So there's a log, whatever that is, base b of x. So a cannot be 0, or you're just going to end up with y equals 0, which we know is a horizontal line, and that's like a degree 0. It's a constant function. B is greater than 0, so just as with exponential functions, right? The base of the exponential function has to be greater than 0. B is not equal to 1, just like exponential functions, right? The base can't be a 1. If it were, we would just end up with the line y equals 1, right? So, and in this course, we will concentrate on log functions where a is greater than 0. Okay, and actually, I think in the review there might be an a is less than 0. You can just ignore that question, or you can do it. It really won't make any difference. But you won't be tested on anything. Part A, the common logarithm. The expression log base 10 of x is known as a common logarithm and is often written without the base, right? So just like that's a square root, right? We don't put the 2 in there. We don't put the index in there if it's a square root. If you just see the word log by itself, then it's a base 10 log, okay? So the two functions, if you see y equals a log base 10 of x and y equals a log x are the same thing, okay? When you see log by itself, it's a base 10 log.
Always 10.
Always 10. If it's not, if you don't see a base written, it's a 10. Like this. You don't see an index there, it's always the square root. Fill in the table of values for each function. So in this case, x is equal to 10 to the power y. So 10 to the negative 2. So what do we do with negative exponents? Put it under 1, really, right? Put it under 1. So you write as 1 over, and then you change it to a positive exponent. So it'll be 1 over 10 squared. How much is 10 squared? 100. So x is equal to 10 to the y is negative 2. 10 to the negative 2 is 1 over 10 squared is 1/100. Okay, if y is negative 1, what is 10 to the negative 1? 1 over 10, right? 1/10. What is 10 to the 0? Or anything to the 0? 1. What is 10 to the power of 1? 10. What is 10 to the power of 2? 100. Okay, so that's going to be graph A. Graph B, y is equal to log x. All right, so we need a calculator. Get out your calculators. I'm just going to clear this. So resetting all. Okay, so you know how it's called the common log? So it has its own key right there, log, L-O-G. So y is equal to log x. So we're going to type in log, and our x is 0.01. And you can close the parenthesis or not, right? And we get negative 2. So I want you to fill in the rest of that table. So just use the log function on the calculator. Log 0.1. Log 0.1. So you fill in that guy. And then for graph C, we're actually doing an exponential function, right? Remember those? Last week, exponential. Wait, last week, this week? Wednesday, remember Wednesday? I don't, apparently. Y is equal to 10 to the x. What is 10 to the negative 2? Well, you kind of did that over there, right? 10 to the negative 2 is 1 over 10 squared is 1/100. So fill in for graph C, which is an exponential function, right? And then we're about to see, hey, these guys are related. The exponential function and the logarithmic function are related. So we have three graphs which we are going to draw. So I'm going to do graph A in red, graph B in green, and graph C in blue. Funny thing is the blue didn't work for about like 5 years. Right? The computer, blue worked. Who knew? Okay, so go ahead and graph those. So we start with graph A. Our x value is 1/100th, and our y. So that means I'm going to be like really, really close, but just a smidge to the right. 1/100th gave me -2. And watch the scale on here. So the scale is by ones, but the labeling is by twos. So 1, 2, 3, 4. Scale here also by ones, labeling by twos. 1, 2, 3, 4, etc. 1/10 gave me -1. An x value of 1 gave us 0. An x value of 10 gave us 1. An x value of whatever next. An x value of 100 gave us 2, but we can't draw that on here, obviously. Okay, that's graph A. Said I was going to do in red. Okay, so here's what, so now before we get to 2 here, right, we have to be out at 100. So we're not going to draw this line so it crosses 2. It's going to climb, but it's going to take from here, from 10 out to 100 to climb this distance of 1. So basically, this is going to be like climbing, but not very climby. And then this thing's going to go down here like that. So if you think about it, 1/1000th would be -3. 1/10,000th would be -4. So this graph is, what is this graph? This is x is equal to 10 to the y. This is the graph x is equal to 10 to the power y. Okay, let's draw the green graph. So when x is 0.01, wait a minute. What do you notice about A and B? They're the same. Okay, so I'm going to draw the green graph just over top. Put down here, what is this? Y is equal to log x. So if they're the same, then those two expressions must be the same, right? And then what's the other graph? Graph C in blue. X is -2. X is and we get 1/100th. So that's just going to be really close there. When x is 1, we get a 10. When x is 2, we get 100. So this, well, that's just your typical exponential function, right? Climbing very fast. So when an exponential starts to take off, it takes off. Right? So nothing much may happen for a while. Tail should be drawn going down here. Okay, remember, we never cross that axis, right? But before we get close to it. So what are the compare? So the word compare, and one of these days, early next week, I'm going to get you your formula sheet because we're going to start to hit the formulas that are on your sheet. Until now, the first 3 units we did, there's really no formulas, right, that you've needed. But when we hit logs, there will be some formulas that we need. So I'm just going to photocopy sheet for everybody to get it for free. On the back, we'll put the directing words. One of those directing words is compare. And so here, saying compare, which means you state the similarities and differences between the two graphs. What's the same, what's different? Okay. So if you see compare on the diploma exam and you just say, well, this is the same as this, and that you leave it at that, then you're not going to get full marks, right? If it's out of 2, maybe you get 1. Maybe you get a half. So similarities, and if there are no differences, then say there are no differences, right? Okay, so what's the same between these 3 graphs? What can we say? If graph A and graph B are the same, right? Like it's not even really a similarity, right? Graph A and graph B are, I'm going to even make it stronger. They are exactly the same. They're exactly the same. They're the same graph. But graph C obviously is not the same. So what's the difference between A or B, or A and graph C? What's different between them? Yeah. OU 30-1. Drop out. Yeah. So what she said is it's the inverse graph, okay, which most of you aren't expected to know, right? But in 30-1, we study graphs that are inverses of each other. But let's list some characteristics, right? So it's like, so what's different? Well, they have different domains, right? So this is exponential function. We know the exponential function, right? It's got a domain of x belongs to the reals. It's got a range of y is greater than 0. So graph, so let's just call it A/B. Graph A/B and graph C, graph, have different domains, comma, ranges, comma, intercepts, right? Like one has an x-intercept and the other one doesn't. One has a y-intercept and the other one doesn't. Okay, so they have different intercepts, both x and y. One sends it, one doesn't. Different asymptotes. That's really not one you'd be expected to know, but just throwing that in there. Is that one too? They have different asymptote lines. And basically, they're completely different. However, what they are, though, is, oh, I never labeled that. Let's label this guy. This guy was y is equal to 10 to the power of x. So you note, where this graph has a y, this graph has an x, and where this has the x, this has the y. So the x and the y values have been interchanged, which, for what, 2 of you, which 2 of you know, when you interchange x and y, you have the inverse graph. They're inverses of each other. So if you want to think of something that everybody knows that are inverses, squaring and square roots are inverses, right? So one operation basically undoes the other. If you square something, you want to undo that, take a square root. If you square root something, you want to undo that, square it. If you have an exponential function, y equals 10 to the x, and you want to undo that, you take the logarithmic function, right? Which you don't know what it does yet. Okay? None of us do. Well, hopefully one of us, but only one of us knows what the log function does, and the rest of you are going to learn that shortly. So these two have the x and y interchange. Okay, this makes them inverse, and you are not responsible for knowing their inverse functions, but this means they are inverse functions. And these two, they're the same, right? These two functions are the same. These two are the same. Okay, so they're just different ways of writing. So if you say, hey, if we have an exponential function y equals 10 to the x, and we interchange x and y, we get the inverse function. And we'll be looking at the properties of that in a moment. We get this inverse function. It's a reflection in this line, right? So imagine this is a mirror. So if you're here and you've got this function, you're looking in the mirror, you're going to see this function. You ever use those mirrors, little red things on, yeah? So if you took a mirror and put it here and look, what you would see is it sort of reflects it on the other side of the paper and you can see through it. And that you would see this line here. Easiest way to think about it is, if this is on a piece of paper, which for you it is, if you folded it on this line, this graph would end up right on top of this graph. Okay, so if you folded it on that line and held it up to the light, you'd only see one line. Depending on how well you drew them, right? Because you're the guy who drew it. But you'd only see one line, right? So one is a reflection of the other. And then these are just two different ways of writing this. Okay, so this is kind of an exponential function, right? But it's got the y in the exponent. This is the same as this. Okay, but it's in the form y equals. Okay, so we're going to look at that. What does all this mean? So, the function y equals log x. Okay, remember, we say log without saying a base. The base is 10. Right? We say y equals log. It's called the common one, and right, you've seen that on your calculator, right? I've got the word log here, right? And obviously, this function must be as important as sine, cos, or tan, because each of them have their own key. So this log function must be important as well. And it has its own key, and it's called the common logarithm. All right, clean the table. So let's look at the properties. Okay, so since polynomial functions, right? So we did polynomials, and we did rationals, right? But we never did this table for rationals. We don't know what the graph of a rational looks like, and we're not worried about it. But for polynomials, we looked at the graph in terms of each of these, right? X-intercepts, Y-intercepts, end behavior, domain, range, etc. We looked at polynomial functions that way, we looked at exponential functions that way, and now we're going to look at log functions. So here's the graph, y equals log x. So remember, these guys here, like this graph is still going down here forever, okay? But these values get really, really small, really, really fast, right? Because we already know this, that's 1/10, that's 100th, that would be 1/10,000. This would be 1/1,000,000, right? Okay, how many x-intercepts? 1. And what is the value of that x-intercept? 1. Okay, so one x-intercept with a value of 1. So for this function, we could say how many, right? So remember with quadratic, you'd say how many x-intercepts? And you'd say, well, if I don't graph it, I know there could be 0 or 1 or 2. Right? If I'm doing a cubic function, I know there could be 1 or 2 or 3. So if we're doing a logarithmic function, right now we're going to say there's 1, and it has a value of 1. Is there a y-intercept? No. Okay, so value of the y-intercept? None. There is not one. What is the end behavior? Q4 to Q1. And is it increasing or decreasing? So Q4 to Q1, and it's going up, it's increasing. Domain? So what can we say about the x? Yeah. So x can't be 0. So that kind of relates a bit to exponential. In exponential functions, we know y cannot be 0. And for here, yeah, what's the range? So set of all y belongs to the reals. So if we look at those two guys, domain and range, we can say that's the exact opposite of an exponential function. Right? In an exponential function, the domain is x is all reals, and the range is y is greater than 0. And that's a characteristic of inverses. Right? So if you interchange the x and the y values in the equation, what you're really doing is also interchanging the domain and the range. Right? Because in the original function, the exponential, x is the domain. But when you interchange, x becomes y, so the domain of the exponential function becomes the range of the logarithmic and vice versa. Right? And we can see that from the graph. All right, what if I throw an a value in here? How does that affect things? So what's the graph doing that's different? Yeah, it's kind of steeper, right? So whereas this one reached 1 at 10, and you think about it, you put a 10 in here, we got out of 1. You put a 10 in here, you'll get out of 1, but then you're doubling it. So it's getting steeper, right? It's got a value of 2. Did that affect how many x-intercepts?
No.
Did it affect the value of the x-intercept?
No.
Nope. So 1 with a value of 1. Now we can think about that by saying, well, if you're putting in, so the x-intercept is when y is equal to 0, right? And so that works, if y is 0, then log x has to be 0. When you multiply 2 times 0, you're just going to get 0. It's not going to change. This won't change this value because it's on the x-axis, right? It has a y value of 0. Is there a y-intercept? No. What is its value? There isn't one. Are you listening? There isn't one. What's its end behavior? This end behavior. Q4 to Q1 and increasing. That's white thing though. Wrong random one. I need clean notes. I gotta save these. So Q4 to Q1 increasing. Domain and range, same. Set of all x, x has to be greater than 0. Set of all y, y belongs to the reals. So these were common logs, base 10, the unwritten, right? The base isn't there, it's a base 10. You can use the log key on your calculator. That's a base 10 log. And we'll figure out what the base means and how that affects things, right, as we go through the log unit. So multiplying it by something didn't really change anything, right? Like none of these properties have changed. It's still Q4 to Q1 increasing, domain and range are exactly the same. There is no y intercept, and there is one x-intercept with a value of 1. All right, let's try a couple other bases. So what if we do log base 2? So here's the graph of log base 2. Okay, so you just got to take it on my word. That is the graph of log base 2. And as we move through the next few days, we'll figure out, okay, why are these values, why they are what they are. So how many x-intercepts? With a value of? With a value of 1. Is there a y-intercept? So its value is none. What is the end behavior? Q4 to Q1, increasing or decreasing? Increasing. Domain? Range? So no change there, right? Oh, something changed here. Y is equal to log base, what's that say? 1/3. Base 1/3. Okay. Something changed. Did that change the x-intercept? No. So what is the x-intercept? Or sorry, how many are there with a value of 1? Okay, so changing the base didn't change that. Does it have a y-intercept now? No, so that didn't change. Did its end behavior change? What's the end behavior? Q1 to Q4. Now, do we really need to say increasing or decreasing? If you're going from 4 to 1, you have to be going up, right? But it doesn't hurt to throw in the word increasing, right? It just helps you remember, okay, just draw this going up. If we say Q1 to Q4, do we really need to say decreasing? I mean, the only way you're going from Q1 to Q4 is to be dropping. But again, adding another word doesn't hurt. Helps us when we're drawing it, just to remember, okay, this is going down. Domain. So still, domain is greater than 0. Range. Y belongs to the rails, right? So it's still going up forever. It's just going up forever very close to the y-axis. Okay? And it's still going down, and we'll cover all the values. It's just as it goes down, it is decreasing, but it doesn't decrease all that fast, right? But it still does decrease. Part B. So there is something called the natural logarithm. The expression log base e, that's a little e, it's a little lowercase e, is known as a natural logarithm and is often written as ln. What's below the log e on your calculator? What does it say? ln. So you can pronounce that ln, or you can pronounce it lon. So it's either a TV show you may or may not like, or it's the grass up front, or out there. Well, it's not really lawn, but so ln or lawn. Okay, lnx or lawn x. I tend to say lawn just because it's like a word, and it's like one syllable. Whereas ln, yeah, say that twice. The symbol e, that little e there, is known as Euler's number. It's named after a guy named Euler, who was a mathematician. It is an irrational number, so irrational like pi or like √2, right? Not rational, so you can't express it as a fraction. Remember rational? I'm trying to forget, you said. You can't forget. Okay, we got a midterm on Monday, November 2nd, and there will be rationals on the midterm. So remember, rationals can be expressed as a fraction. Irrational cannot be expressed as a fraction. It equals 2.71828182824. You don't need to write next. That's just more stupid stuff. Why are you showing us this? You don't need to know that. So 2.71828. So the two functions, if you see a, because we can always have an a in front, log base e of x, and a ln or ln x, they're the same thing. Okay, so if you have to do a base e log on your calculator, which you will, you're going to use the ln key. If you see ln written and you have to change it to write it with a base, you would write it as log base e, where e is that number. You don't really have to know. Here's the only thing you really have to know. It's bigger than 0. Or sorry, it's bigger than 1. So it's going to behave, it's somewhere in between this log base 2 and this, which is a log base 10, right? It's a log base 3. Whereas what we've seen here, when the base is less than 1, all of a sudden we got the graph going like this, where it's going Q1 to Q4 and it's decreasing. Okay? That will make a lot more sense in the days to come. So just know it's a number bigger than 1. So it looks like log base 2, log base 10. Okay, kind of in that thing, and it's got characteristics. So number of x-intercepts. Okay, is this any different? Okay, it's no different than a base 2 log or a base 10 log, right? So as long as the base is greater than 1, what's different, its steepness is a little bit different, right? But that's it. Otherwise, it's got all the exact same properties. So it's got one x-intercept with a value of 1, a value of 1. Why do they all have a 1 will be a question we answer soon. Is there a y-intercept? No and none. And behavior? Domain? No. 0. Range? And if we throw a number in front of it, what changes? Yeah, slope, right? It's like less steep now because I put a half. If I put a 10 in front, it would just be more steep. Okay, but would any of these guys change? The answer is no. Okay, so putting a number in front doesn't change the fundamental properties. Be the same deal here. If I threw a 10 in front of this, this would just fall more steeply, but all the characteristics would be the same. It would not change any of them. So let's just go fill that in. So 1 with the value of 1. No y-intercept, none. Q4 to Q1, increase it. Set of all x is greater than 0 and belongs to real. Set of all y belongs to real. In summary, the common logarithm y equals a log, just see log by itself, what's the base? Base 10. And the natural log function a log x, where a is greater than 0, has, so our a value will always be positive, right? So in this course, except for one review question, right? And you can just ignore that one review question. I was looking through and it's like, oh, that was there. So how many x-intercept? Located where? Y-intercept? None. We're just going to say no y-intercept. And behavior from Q4 to Q1 when what? When a is greater than 1. A is greater than 1. It's going to look like this. Q1 to Q4 when? Less than 1 but greater than 0. So when a is between 0 and 1, a between 0 and 1. And if you mark the x-intercept on both those graphs, it's always going to be at 1. It's increasing when? So when a is greater than 1, when it's going from Q4 to Q1, it's increasing, it's going up. It's decreasing when? Yeah, so just say between 0 and 1. I'll translate it. So 0 less than a less than 1. Okay. So when we're putting a number, we're saying you're in between two numbers, and we always list it with less than or equal to sign. But the low value is less than or equal to. So in this case, strictly less than, right? Not equal to. But we use less than or equal to. So the low value is less than or equal to the variable, which is then less than or equal to the high value. Okay. So that's how those things are listed. Domain is, and the range is, hard to see. Okay, great. Which of these graphs are logarithmic, and explain how you know. So the first one logarithmic. Yeah. Okay. How do you know? Okay. So logarithmic is no y-intercept. Anything else? Yeah. So Q4 to Q1 decreasing, which means that what? Yeah, your A value is between 0 and 1, right? So it's a log function, right? We can recognize that. Going and here are some reasons, right? So on the diploma, so you've got 2 written questions on the diploma, right? Each question has 4 parts. The first part is worth 1 mark, and is usually just a simple calculation or something, maybe run a regression, just something that really doesn't require a lot of algebra. Maybe just a minor bit of algebra or just stating the domain of something. They show you something and say, what's the domain? That's worth 1 mark. And then you have 3 other parts to the question worth 2 marks each. So they generally require some work. You got to show something, right? That's the whole point. Like, why do written if there's no work? One of them will usually require some sort of an explanation. So it might be, explain this particular thing. Like, explain how you know. Is it logarithmic? If you just say it's logarithmic, you might get 0 marks, right? It's like, is this logarithmic? Why? Justify. See the word justify. When you get your formula sheet, on the back of the formula sheet, I will photocopy all of the directing words. Don't memorize them, but just be familiar with them, right? And just understand any of them you see mean you got to do something. You got to show all your work. You've got to explain something. You got to compare, okay, which is similarities and differences. What's the same? What's different? Is this logarithmic? No. No. What is it? Yeah. No. It's exponential. Okay. And you could give some reasons, right? It's Q2 to Q1 increasing, which means that B is greater than 1, right? Base. So for the base, we use B. Is this logarithmic? Yes. Why? Yeah, so no y Q4 to Q1 increasing. No y-intercept. Y-intercept. An x-intercept of 1. You write that over here too, right? You get an x-intercept of 1. In this case, then A is greater than 0. A is greater than 1. It is greater than 0, but that's not enough, right? It's greater than 1. So for logarithmic with an x-intercept of 1, you can't just say x-intercept of 1, right? I mean, I could draw a quadratic that's got an x-intercept of 1. I could draw a cubic that has an x-intercept of 1. So that by itself is not enough information, right? Like, don't try and cheap out on your explanation. No, well, it's got an x-intercept of 1, therefore it's logarithmic. It's like, nah, that's not what makes, like, that's one of the characteristics, but that's not it. So you need to give a bit more. It's going from Q4 to Q1, it's increasing, okay? That adds to it, right? So, well, some of them are the same, right? But end behavior is just one of the characteristics, right? So this end behavior tells you it's not exponential. But Q4 to Q1 decreasing, okay, that wouldn't be a cubic, right? It can't be a cubic. That would not be, well, you could draw a quadratic that does that, right? So here's a quadratic which is going from Q4 to Q1, and it's decreasing. So again, like, one characteristic alone is not enough. Put together 2 or 3 characteristics, you've got enough, right? So, you got 6 hours on the diploma. Come up with 2 or 3 characteristics, right? Don't just cheap out and say, I'm just going to give you 1. Because they're going to say, and for marks, you're going to get none. State the properties of each function. So what is the x-intercept of this What is the x-intercept of this? What is the x-intercept of this? How many y-intercepts are there? And, okay, fill in the rest. See if you're paying attention. Use a pencil. Have an eraser handy in case you weren't paying attention. So at this point, right, it's like everything else we studied, it's like, here's the characteristics of the equation. The equation tells us about the graph, right? Whether it's quadratic, right? Y equals 5x squared. Oh, positive, so it's going like increasing in Q1, and it's going Q2 to Q1. It's increasing in both of those. So I can look at this. So we should be able to look at an equation and basically fill in this chart, right? Okay, look, here are the characteristics. I see that equation, I can tell you the characteristics. If I need to, I can graph it. Note, you can't graph this one yet. You don't know how. You will. But for now, you don't know how. That's okay. We don't have to graph it to know, right? We can look at this and say, oh, yeah, because of that, since the a value, right? The a value between 0 and 1 tells me, right, really, what's the only difference here, right? Is it Q4 to Q1 or Q1 to Q4? Everything else is the same. Domain. 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 Range. 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 That's it. Here, let's pop in here. So let's just take a look at this. Log. So I want, actually, no, I can back up on that. Back. So in decimals, there are some functions. It's a miscellaneous function. This is log, and it will give me a base. Okay, so here I can put in the base. So if I put in A, we'll type in an A. Tab. Okay, let's go in here and we'll put in the X. So it says add a slider for the base, right? Okay. And I don't want negative 10, right? So our A value, we said we're going to keep it positive. Okay, and then if I press play, we can see, yeah, okay. I mean, as the A value, oh, okay, wait a sec. As the base is going higher, the graph gets less steep. But when it goes between 0 and 1, it's flipping, right? Now it's Q4 to Q1. Base gets higher, graph gets less steep. And then all of a sudden, it flips when the base is between 0 and 1. And that's where we'll end it.